Alright, up to now we have talked about a composition, its underlying track file resources and how these assets relate. We've touched on the word delivery but never really got into the aspect of how these compositions actually get to their intended destination and how they should be packaged to ensure successful delivery from A to B. With that in mind, welcome to our section on packaging and file segmentation, where we will discover exactly how a composition can be bundled into a manifest and how it occupies the file system, in layman's terms, the hard disk drive it sits on. A lot of this responsibility resides with the packing list, an XML file that essentially acts in part as a manifest file for a composition. So to start, we need to define what a packing list is. A packing list is an XML document that consists of metadata pertaining to the track file assets, composition, and auxiliary data resources. It provides a means to authenticate and verify the integrity of the resources delivered in the package. Such metadata is an asset ID, a hash value, file size, and file name. The keywords here are authenticate and integrity. Now, let's take these metadata values in the context of how they are applied to a CPL and go through the verification process in a step-by-step manner. As you can see here, the asset ID of the file is a UUID. It registers the file to have the following hash value. It knows it to have a file size of 15,393 bytes. It has a MIME type association of being an XML document and has a file name as follows. I'm aware that this may be the first time you are seeing the word hash. Hashes are one of the most fundamental requirements when it comes to the interchange of assets in IMF. The hash value, which in this case is a base 64 encoded binary representation of a SHA-1 calculated message digest value. What's a message digest, you might ask? Well, a message digest is a cryptographic hash function designed to protect the integrity of a piece of data or media in order to detect changes and alterations to any part of a message, which in layman terms translates to if somebody tampers with the data of the file by calculating the digest of that file and comparing it against the trusted source of that digest, you will know. The term trusted source here presents me the need to mention XML document signers, which is the signing of XML documents such as the CPL, PKL, and Sidecar Composition Map with X509 certificates. However, this will take us down the road of encryption in IMF and managing cryptographic identities as a means to facilitate the exchange of encrypted assets within an IMF ecosystem, which is out of scope for this tutorial series. Though I do cover it in my advanced course, so be sure to request that if such a topic is of interest to you. Okay, back to it. So how is this hash value calculated? Simply put, we calculate a SHA-1 message digest of the asset and encode its binary representation as base 64. This is the exact same process a system which the packing list presents the asset to should perform in order to verify the asset. What happens is 1. The asset is confirmed to actually exist within the package. 2. The asset's file size is in fact, in this case, 15,393 bytes. And 3. It is an XML document and does have the asset ID as denoted in the PKL. The hash value is then calculated for the asset by the system, and with all things going well, it should calculate the same value, which in turn then verifies the authenticity of the assets and authenticates it to be ingested into the system. So there you have it. The packing list's responsibility is to list the available assets and provide the means to verify the authenticity of an asset's integrity when it comes to presenting it to an IMS system for ingest and processing. Of course, there will always be more questions. For example, but the packing list doesn't contain a file path. How does the system know where that asset actually resides? That responsibility falls to the asset map, which, by definition, an asset map is an XML document that consists of reference metadata which maps the asset ID value to the corresponding asset and where its location resides within a local or peripheral file system. It is commonly referred to by its acronym AM. It basically tells the system, here's an XML file with an absolute path that is relative to where I am as an origin. It has this ID and occupies this much space within the file system. So let's break down the relationship of all files with some visuals. Let's start with the CPL, which gives the order to the image, audio, and data track file resources through the referencing of these resources from within the file itself. Alongside this file, we also have the Sidecar Composition Map, which, again, orders the auxiliary sidecar files. As already mentioned, These files contain information pertaining to the CPL, which the sidecar in turn references, ensuring that a relationship is bridged to the respective CPL that the sidecar file is relevant to. Then there is the OPL, which too references the CPL via its ID. And of course, the PKL, which holds the file size, asset ID, original file name, and hash value for each asset. Then finally, at the top level, we have the asset map, which, as just discussed, maps the ID of each asset to its file name within the file system so that when the PKL is processed by a system, that system can then proceed to work explicitly on an ID basis with each asset. Everything accumulated here together creates a package, or, as we now commonly refer to it, an interoperable master package. Before we move on, I want to make a charitable mention to another file called the volume index, which unfortunately does not get its own presentation and is not widely used for the purpose to which it was originally designed to service. This was that it presented the means to identify assets within a file system via the asset map if those assets were located across more than one volume.